Number 15, almost done. We're given a tennis ball being thrown down from a given height, 4.5 meters, towards the ground. We're given the initial speed. What coefficient restitution is required so the maximum height after the bounce is equal to the original height? Okay, so key word here, maximum height, means that's going to be y velocity is going to be 0. To draw a quick sketch, we have a tennis ball starting up here, 11 meters per second. Okay, and it's at a height of 4.5 meters. Okay, so we'll draw our height in here. Okay, after the bounce, we'll have the tennis ball again. Okay, its velocity is going to be 0. It's still going to be at that 4.5. meter height. So let's obviously use our ground as the datum. So let's work backwards. If we're going to get a maximum velocity of maximum height of 4.5 meters, we can use conservation of energy between this location to find this velocity after the bounce. So I'm going to call that we'll just call this state 1, this state 2 right before the bounce. Okay, this state 3 and this state 4, just to keep everything straight. So we'll have the ball before the bounce, okay, the ball after the bounce coming back up. This is going to have some velocity here. Okay. We want to eventually get to where we find the coefficient of restitution. Okay, so that's what we're trying to find, and that applies during the collision, so that's actually dealing with the velocity 2 and velocity 3. So let's write our coefficient restitution equation so we know what we're after here, and that's going to be the velocity of the ball after the collision, which we called v3, minus the velocity of the earth, which is effectively 0. Okay, and the top term has a negative on it, and that's over the velocity before the collision of the ball minus the velocity of the earth. So let me just write these in to make it a little more clear that that's dropping out. Okay, so there's a coefficient of restitution. Instead of using a prime up here, we're using 3 for after and 2 before. So we're really looking for velocity 3 and velocity 2. Okay. So we use conservation of energy between state 1 and 2, where the ball is just going downward. COE between 1 to 2. And we'll have some initial gravitational potential energy, mgh plus 1/2 mv squared is going to be equal to our final kinetic energy, 1/2 m, and that's v1 squared, and this will be v2 squared. Okay, so we can solve for v2 in this equation. The m's cancel out. V2 is going to be, let me go ahead and plug the numbers in just to keep things straight here. 9.81 times 4.5 plus 1/2 of 11 squared equals 1/2 V2 squared. V2 is equal to, sorry about that, let's see, 9.81 times 4.5 plus 0.5 times 11 squared times 2 square root. So V2 is 14.47 downward. So I'm going to write that as a negative just because I know it's downward. Okay, and we'll use conservation of energy going from 2 to 3. Excuse me. 2 to 3 is the collision. So 3 to 4 to find the velocity 3 that's required to get up to that height. So before, at velocity 3, we just have some kinetic energy, 1/2 mv3 squared is equal to mgh. Okay, so we'll have, again, masses cancel, so 1/2 v3 squared is equal to 9.81 times 4.5, and v3 will come out to be something 9.81 times 4.5 times 2 square root. 9.396. Okay, and that's going up. Alright, so we can then calculate E from those two numbers. It's going to be a minus 9.396 over minus 14.47. So we'll take that number divided by 14.47, 649.649. E is unitless, it's a ratio of relative velocities, so final answer 0.649.